Okay, this is mole calculations tutorial B. Okay, so I'm just going to finish off where we left off. I'm going to start off where we finished off last time. Can't get my words out. Okay, so we left with this balanced equation. To balance this equation, okay, so I'm just going to go by our normal method. I'm going to say over here, carbon. There's one carbon, so this is my reactant. By hydrogen, there are. That doesn't work. Hydrogen, there's 4 of those, so I'm going to put my 4 there, and my oxygen, there we are, 2 of those oxygens. Lovely. So let's go over the other side. Let's look at the product side. So we need to count up over here. As you can see, there's one carbon in the carbon dioxide. There's 1. Hydrogens. Let's have a look at hydrogens, that colour. And hydrogens, we're looking for, and there's 2 of those, so 8, there's 2. And then we're going to look finally at our oxygen. Okay, now be a little bit careful here. We've got 2 oxygens and another oxygen. So we have 3 oxygens all together. Okay, so where am I going to start? We know that we've got imbalances everywhere. I'm probably going to start with the hydrogens first, and I can see an easy fix on the hydrogen straight away. And I would suggest when you see this type of equation, this is known as the complete combustion of a hydrocarbon, I would always start with the hydrogens. Okay, so having a look here, got the 4 hydrogens and the 2 hydrogens. So I'm going to get round that problem, I think, straight away by putting a 2 in front of my H2O. So 2 times 2 is going to make it into 4 of those, yes, which is great. Then let's see if anything's happening. Oh, and we can tick that off at the same time. So, I'm trying it as I go along. If I make a mistake, it's okay. I can come back, start again. But that looks okay to start with. Looking at my oxygens now, I've got my 2 here still, but don't forget that big 2 means everything in the formula is times by 2. So I actually have 2 of those oxygens as well. So 2 and a 2, that adds up to 4 oxygens now. Now actually, that's helped me out a bit, hasn't it? If you look on the reactant side, on the left hand side now, I've got my 2 oxygens. Now to get round my oxygens, if I put a big 2 there, I now make that 4. I have now sorted it out. My carbons haven't changed, and all is good. Okay, maybe we'll just try one more, shall we, while we're at it. Okay, let's try C2H6 plus O2. Again, it forms carbon dioxide. The carbon and the oxygen react together form CO2, complete combustion, and we're going to get the hydrogen and the oxygens react together to form water, H2O. Let's see where we get this time. Now we're going to see our carbons on this side here. Now we have 2 of them, C equals 2. Hydrogens are equal to 6. There's 6 hydrogens on the bottom here, and there's 2 oxygens. O equals 2. Go on to the product side. We have over here, well, we've got 2 carbon equals to 1 of them over here. Hydrogens, we know how hydrogen equals, there's 2 of them, and oxygens, there are 2 plus 1 more, there are 3 oxygens altogether. So now we need to sort this one out. So my kind of rule was, I started with hydrogens before. Next little top tip, if you have to do carbons as well, do the carbons, then do the hydrogens, then we can sort oxygens out at the end. Okay, we will come get round it. So let's try it. Okay, so we've got carbon here, 2 of those. I've only got 1 over here, so therefore I'm going to change the formula over here. I'm going to put well, not formula, I'm putting the big 2 in front. So I have 2 carbons. There we go. And don't forget, I've done something to my oxygens now. I have 2 plus times 2, which is 4, plus 1 more. I actually have 5 oxygens. So I will just remind myself that I've done that to it. But carbons are, at the moment, are good to go. Now the next thing I said to do was try the hydrogens. Okay, because that's quite easy, because we've got a 6 and a 2. So we've got an even and an even. And if I put a 3 in front of my H2O, that will make that 3 times the 2 will make that 6. So I happily sorted my hydrogens out. Now that, and let's just see what that's done to the oxygens. Now we had 2 and a 2, that's 4 oxygens, plus 3 oxygens. So I believe now we have 7 oxygens. Okay, so there's my 7 over there. Let's go back. What we're going to do with this oxygen, we've just got the 2 oxygens here. Now it might upset some people, but you're allowed to do this. We're allowed to use half numbers to make this work. So if 2 goes into 7, 3.5 times. So I do 3.5 times 2. I will make 7. Nice and easy. Done. If you don't like halves, then you can get rid of the half by timesing it all through by 2, and that would do, so it would be 2C2 86 plus 7O2, 2 times the 2, 4CO2 plus 6H2O. Okay, hopefully that made some sense. They are a little tricky, trial and error, do your best on them, and obviously if you're stuck, come and have a chat and we can work through more together, but they don't get much more challenging than these ones at the bottom. Okay, so next part to our tutorial is something called relative atomic mass. You may have come across this term before, but let me show you on the periodic table. There we have it. We've got our periodic table. You can't really see it that clearly, but on all the elements you'll notice that you've got a big number and you have a small number, ions 56 and 26. The 26 is the atomic number. The bigger of the two numbers known as the mass number, but it's also called something else. It's also referred to as this thing called relative atomic mass. Okay, so if we were to look on the periodic table, we're going to look for the smallest atom that there is. Okay, we know atoms are incredibly small, they're very, very difficult to weigh, so we get round it by trying to compare one atom to another. Now if you might have noticed that hydrogen here is our smallest number. Okay, it's the smallest atom, so I am going to try to represent it as this slippery little sucker. I've got my little hydrogen here. Yes, now it's much easier to start comparing each atom to each other rather than using masses, and that's what we're going to do. So with this in mind, let me grab another ball. Let me try to represent this one. Now this one, I believe, I feel it, it's about 12 times heavier than the hydrogen atom. So which of the elements do we think this could be representing, this larger atom here? And if you noticed, carbon over here has got a relative atomic mass of 12. So I'm kind of saying that carbon in its essence is kind of 12 times heavier than the hydrogen. So that's my hydrogen, there he is, and that's my carbon, and it's 12 times heavier. Yes, okay, so let's try again and try to see another example of that. Let's take something that got an even bigger representation of an atom here. Here we are, big boy on the block here. Now I believe this atom here, this larger atom, is 12 times heavy. It's 23 times heavier even than my hydrogen atom that's wobbling around there. That's my hydrogen just here, 23 times heavier. And if you can spot it on the periodic table, focusing not great, I think that's representing sodium, because it's kind of 23 times bigger, yes, than my hydrogen atom. Okay, so it's all the word relative is meaning comparing sizes of atoms to each other. So that, in essence, is what we mean by that term. So let's write that down. When we've got something called relative atomic mass, it's comparing the mass of one atom to another, and the reason it's much easier to do that because they are so small. If we had to weigh them in grams, it'd be such a small number, it'd be really difficult to work with that. So we say relative atomic mass, just comparing one. So we're going to say hydrogen is smallest or lightest atom. Okay, assigned a value, assigned an RAM equal to 1, and then we can say that, say for example, carbon 12 up the top there, carbon 12, we can say that a carbon atom, the relative atomic mass of carbon is 12, so a carbon atom is 12 times heavier than a hydrogen atom, right? So, and likewise with the sodium would be, sodium is 23, it's relative atomic mass of 23, and it's going to be 23 times heavier, 23 times heavier than the H atom. Okay, so that's what we mean by the term relative atomic mass. It can be referred to as mass number as well, which we talked about in the atomic structures video, but it's a start, it's a good way of going. There is a slightly different, the official definition for this, if you're doing A-level chemistry, is that the relative atomic mass of any element is the average mass. Now the word average is referring to isotopes, and that we haven't gone into the murky world about isotopes, but if you're doing it at GCSE, you will have come across isotopes. So every element has a different mass number, so you take the average of all those different mass numbers. So the average mass of one atom of an element compared to 1/12 1/12 of the mass of an atom of carbon 12. And what that basically means is, if you do a 12th of 12 of carbon 12, yes, a 12th of a 12 equals 1. So that's always comparing everything to 1, and hydrogen is the value of 1, relative atomic mass. Why they've done that is probably because hydrogen is a gas, and a gas is much more difficult to weigh than a solid, as is carbon. So it's probably easier for them to find the mass of a carbon and then divide it by 12 and compare everything to carbon than it is to do with hydrogen. But many years back, hydrogen was always compared to hydrogen, so it's a slight difference in what they've done nowadays. But as long as you remember, hydrogen is the smallest atom and everything's kind of compared to that, we don't go too far wrong. The other thing that we come across at this stage is something called also relative formula mass. It's also can be referred to as relative molecular mass, and they sometimes refer to it as capital M R as well. So there's a number of ways to represent it. We go away with relative formula mass because relative formula mass takes into consideration the mass of ionic compounds and covalent, whereas relative molecular mass is really kind of only referring to covalent molecules. So I think the official term now for it all is known as relative formula mass. So what does that mean? Well, you could be asked to find the RFM. Yes, so the RFM, relative formula mass, they abbreviate it all the time in science, RFM of carbon dioxide. So what we're going to do, we need to count up the number of atoms in this molecule. We've got one carbon atom, got 1 times carbon, and we've also got, add to that, we've got 2 lots of oxygen atoms, 2 times the O. So let's have a look on our periodic table and find out what those values are. So we found carbon, we might remember, carbon relative atomic mass of 12, so we've got one of them, so it's going to be 12 plus, and oxygen, there's 2 lots of oxygen, and if you see here, oxygen's got a relative atomic mass of 16, so it's 2 times 16. So you know, your maths is light, but I think that adds up to 44. Alright, so our relative formula mass of CO2 is 44. It's quite simple, isn't it, to find relative formula mass? You just add together all the relative atomic masses within the formula. Don't forget to times it out by the small numbers underneath each of the elements. Let's try one more, a bit trickier. Relative formula mass of calcium nitrate. Now you may remember we've used, when we did formula writing, we used brackets, yes, because we needed 2 lots of the nitrate, negative ion, to cancel out the 2 plus of the calcium. Go back and look at ionic bonding to know where the formula came from. But what is the relative formula mass of calcium nitrate? So let's have a look. We got 1 lot of calcium, 1 times Ca, okay, plus, now be careful here, you've got 2 outside the bracket. Now everything in that bracket is times by that number, so it's 2 times the nitrogen, 2 times N, yes, plus, let's not forget the oxygens, got 2 lots of 3 oxygens, so we're going to have plus 6 times the oxygens. Now you'll need your periodic table, you'll be provided this all the time in the exam. Sometimes in the question they give you the relative atomic masses for it, but calcium is here. Now calcium has got a relative atomic mass of 40, the bigger of the 2 numbers, so it's 40 times heavier than the hydrogen atoms, but it's going to be one of those, 40, plus 2 times the nitrogen. Now nitrogen is over here, and nitrogen's got a relative atomic mass of 14, so we're going to do 2 times 14 plus 6 times our oxygen. Now our oxygen, as we saw before, was 16, so I'm going to put 6 times 16, and I've done the brackets. I'm not much of a mathematician, but I know it's important to keep it in brackets and do them separate and add it all together, and you should get, when you add it all together, 164. So they will expect you in the next tutorials, have a practice at some of these, because we will expect you to be able to do relative formula masses quite quickly and easily. It isn't that tricky really, just so that we know. I think I might have even forgot to say it, but I kept referring to it. Relative atomic mass, we abbreviate it to RAM, and you can see I've just been lazy and been writing it as RAM all the way through after that, yes. Sometimes they call it AR as well, so just don't get confused by any of that. Good luck, have another look through it, make sure you're all happy with that, and then we'll come back to it in I'll keep referring that into the future tutorials. Alright, so now we've got balanced equations out the way, now we know what relative atomic mass and relative formula mass is, we can hopefully crack on with the main part of mole calculations. Hopefully next session I can tell you what actually is a mole, try to explain it in its simplest form. Okay, thank you so much, talk to you soon.